Real exam questions. This is question 25 about the design of columns. When checking the load-bearing capacity of a reinforced concrete column, the method of moment magnification factor may be used to estimate the second-order moment and prove the formula below. Consider a rod like this, subjected to a load NED with an eccentricity of E, and the resisting forces of bending, or the resisting bending moment, is M equals K times the angle of displacement. So the resistance is proportional to the angle of displacement. The displacement here is X, and the eccentricity is E, and the length of the total height is L. Now, the stabilizing moment is, like we said, K times theta. The destabilizing moment is, of course, NED with its total eccentricity E plus X. We assume that theta is small, so that theta is in fact the tangents. Theta is equal to X over L, but when theta is small and it's expressed in radians, then theta is equal to X over L. At equilibrium, stabilizing bending moment must be equal to the destabilizing bending moment, or K times theta with theta X over L equals NED with its total eccentricity. We rearrange it for X, and K over L, we know that K over L is equal to N critical. It is the bending moment, or it is the normal force on the rod, that with this value of the normal force, there is just equilibrium. Then this can be expressed as follows, that the total or the deflection X is equal to the initial eccentricity of the normal force, and with a factor, with multiplied by a factor, which is equal to NED divided by the difference of N critical minus NED. We see that when N critical, or when NED approaches N critical, then X will be infinity. So that is, of course, there is no equilibrium possible. The second order bending moment is by definition the design value of the normal force multiplied by its eccentricity. So E2 is a second order deflection, and in our case, it's X equal to X. So the second order bending moment is NED times X, but we've seen X is proportional to E1 with this factor. We can substitute X into that. And now we can first divide this form by NED in both cases. So you got 1 there and N critical over NED minus 1. Then we substitute, because you got NED times E1, which is the first order bending moment. So this becomes, then the second order bending moment is depending on the first order bending moment times this factor, or total bending moment is M1 plus M2. And you can write it in this way, and that is the relationship that we have proven. Now, this is what we have proven, but now what we have proved. Now M, the bending moments, if we make it equal to the MED, M1 is M0 E, and N critical is NB, then an NED is NRD at the limit. Then we see if we substitute those values in here, then you can you have exactly this expression, which is the same. There is a coefficient beta m, and beta m is the distribution of the first and the second order bending moments, and is more or less equal to p squared over 8. So this is a refinement of the formula.